So now we're going to talk about Clausius Clapeyron relationship. And this seems pretty out there, but it's going to show up several times during the course. And so the main idea is that if we have different liquids, then we talked about the intermolecular forces. The stronger the intermolecular force, the higher the melting point, boiling point, all those things associate with it. So when you're in the liquid phase, you have a vapor pressure. And so the amount of vapor pressure is dependent on the intermolecular forces. And then it continues to increase as we increase temperature. This is universal throughout. But something magical happens when the vapor pressure equals atmospheric pressure. And we call this boiling. And this is an easy property we can measure. So what the Clausius-Clapeyron relationship does is it relates that vapor pressure at one temperature to a vapor pressure at another. Sometimes they're just random points. So temperature 1, temperature 2, pressure 1, pressure 2. And sometimes then they just say the normal boiling point. And then so we just have a temperature. And the kind of meaning is that pressure is 1 atmosphere, 1 atm, or 760 millimeters of mercury. That's all this equation does. And so the vapor pressure is related to the heat of vaporization and the temperature. And the main relationship is this. Okay, so we have ln of P1 over P2, or ln of P1 minus ln of P2. So remember that kind of math in rearranging and solving is pretty unique. So you definitely want to practice that. And we have the heat of vaporization over R. And now we have our second kind of thing is that the units of this is usually kilojoules, and R has the units of joules. So you'll need to do that conversion to make these two match. Doesn't matter which way, because we're going to divide it and cancel it. All right, and then we have this inverse relationship with temperature. And again, we need it to be in Kelvin. It's often reported in Celsius. So a bunch of little pieces, so high level kind of problem with it. Now, when you go look on the internet, you'll find a lot of different versions of it because of what happens then. If we have ln of P1 over P2, like I told you, you could subtract those. That's all ln does, relates multiplication, division to addition and subtraction. So, and notice here is that sometimes people put the minus in the form, and all that does is flip T1 or T2, but it could equally flip P1 and P2 here. All right, so as you just need to pay attention to it. The nice thing, though, is that if we go back to this trend, we know that as we increase temperature, vapor pressure should go up. And I believe if you see that trend, just flip T1 and T2, or vice versa, P1, P2, one of those, but normally flip T1 and T2, and you'll find then as long as it matches this trend, you should be golden as long as you took care of the units here. All right, so heat of vaporizations in kilojoules. So there's an example problem. You can do it, and I'll walk you through the process, and you can see. So kilojoules to here, why? To get it to be in joules. Okay, everything else should be rather straightforward. A nice, simple video.